Welcome all of you. We are going to start the paper second, that is calculus 2, and it is the continuation of calculus 1. So in calculus 1 there are the topics that limit, continuity and sequence, and now we are going to study in this paper calculus 2. The first topic is differentiation. So we are going to start the chapter number 1, that differentiation. So let f be a real valued function defined on the interval ab, and c is the point of ab. Then derivative of f at the point c is what? F dash c is what? Limit x tends to c, f of x minus f of c divided by x minus c. So already this chapter differentiation is in your 12th syllabus, 12th science syllabus. So what is the definition of derivative? Derivative of the function at point c is what? F dash c is equal to limit x tends to c, f of x minus f of c divided by x minus c. Or in another form, the definition is what? F dash c is what? Or f dash x is what? Limit x tends to 0, f of x plus h minus f of x divided by h. So both the definitions are same. That is, f dash x is what? Limit x tends to 0, f of x plus h minus fx divided by h. So both the definitions are same. So this is the definition of the derivative of the function f at the point c. So this function is defined on this interval a, and c is the point of that interval. So the derivative of f, obviously with respect to x at point c, is f dash c is equal to limit x tends to c, f of x minus f of c divided by x minus c. So if limit does not exist, so here the wording is what? Wording is what? If limit exists. That is, if this limit does not exist, then we say f is not differentiable at x is equal to c. And we know that when this limit does not exist, if right hand limit and left hand limit are not equal, that is, if limit x tends to c plus fx minus f of c divided by x minus c, and limit x tends to c minus f of x minus f of c divided by x minus c, these two are not equal, then we say this limit does not exist. And if this limit does not exist, then we say f dash c does not exist, that is, the derivative does not exist. F is not differentiable at x is equal to c. So here the definition of right hand limit, f dash c plus, what is the notation? Right, plus at the bottom of the f is limit x tends to c plus f of x minus f of c divided by x minus c, that is right hand limit. And f dash c minus is limit x tends to c minus f of x minus f of c divided by x minus, that is left hand limit. And we know that this is right hand limit, left hand limit, these two are equal, then we say the function is differentiable. And so f dash c exists, means f is differentiable at point x is equal to c if, or we say f is differentiable at x is equal to c if f dash c plus is equal to f dash c minus. This is called right hand derivative, and this is called left hand derivative. That is, if the right hand derivative at point c and the left hand derivative at point c are equal, then we say the function is differentiable. That is, this right hand limit and left hand limit are equal, then this limit exists, and if this limit exists, then f dash c exists. So in another form, what we say, if right hand limit and left hand limit are equal, then we say f dash c exists, or f is differentiable at x is equal to c. Show that fx is equal to mod x, x is not equal to 0, is not differentiable at x is equal to 0. So this is the example of not differentiable. So fx is not differentiable. What do I have to prove? Fx is not differentiable at point x is equal to 0. That is, we have to show f dash 0 plus is not equal to f dash 0 minus. That is, the right hand derivative at point 0 is not equal to left hand derivative of f at point 0. So we have to show f dash 0 plus is not equal to f dash 0 minus. And what is f dash 0 plus? F dash 0 plus, by using this definition, f dash 0 plus is what? Limit x tends to 0 plus f of x minus f of 0, because c is now 0, divided by x minus 0. This is f dash 0 plus. And limit x tends to 0 plus means limit x tends to 0 and x is greater than 0. That is, x tends to 0 plus means x tends to 0 from right side of the 0. That is, all the values of x are greater than 0. and fx minus f of 0 divided by x minus 0. So what is fx? Fx is mod x. Fx is mod x. So write mod x minus mod 0. F of 0 is what? Mod 0 divided by x minus 0 is x. And so limit x tends to 0, x is greater than 0 means, so here the meaning x tends to a plus means x tends to a and x is greater than a. That is x tends to a from right side, and x tends to a minus means what? X tends to a and x is less than a. That is x tends to a from left side of the point A. So we have mod x is now x because x is greater than 0 divided by x minus 0 divided by x, and then x by x is 1. Mod x is x if x is greater than 0, and mod x is minus x if x is less than 0. Look, we know that mod 5 is 5, but mod minus 5 is not minus 5. Mod of minus 5 is what? Minus of minus 5, that is plus 5. So mod of x is minus x if x is negative. So here x, mod x, value of mod x is now x because x is greater than 0. Why x is greater than 0? Because x tends to 0 plus, means x is greater than 0. And so mod x is x, and the x by x is 1, and limit of 1 is 1. So right hand derivative, that is f dash 0 plus is 1. Now we have to find the f dash 0 minus. What is the definition of f dash 0 minus? This is the definition. F dash 0 minus. Limit x tends to 0 minus f of x minus f of 0 divided by x minus 0. So f dash 0 minus is what? This limit x tends to 0 minus fx minus f of 0 divided by x minus 0. And what is the meaning of x tends to 0 minus? Means x is less than 0. And fx is mod x minus mod 0 divided by x minus 0. And limit x tends to 0 minus means x is less than 0. And if x is less than 0, then mod x is what? Minus x. If x is less than 0, then mod x is minus x. Because what is mod of minus 5? Mod of minus 5 is minus of minus 5, that is plus 5. We know that mod of minus 5 is plus 5. Why it is plus 5? Because mod of minus 5 is actually minus of minus 5. So, and that is plus 5. So mod of negative number, if the number is negative, x is less than 0, then its mod is minus of that number. What is mod of minus 5? Minus of that number. Minus of minus 5 is plus 5. So mod x is minus of that number if x is negative. So we have mod x is minus x minus 0 divided by x, and minus x by x is minus 1. And the limit of minus 1 is minus 1. And therefore, left hand limit is what? Is minus 1, and right hand limit is plus 1. That is f dash 0 plus is not equal to f dash 0 minus, and therefore the function fx is equal to mod x is not differentiable at 0. But this fx is equal to mod x is continuous at x is equal to 0. Why is continuous? Because fx, when fx is continuous at x is equal to a, if limit x tends to a, fx exists and is equal to f of a. And when this limit x tends to a, fx exists, if limit x tends to a plus fx is equal to limit x tends to a minus fx, that is right hand limit and left hand limit both are equal, then we say the f of a, limit fx as x tends to a exists. So when this limit exists, these two are equal, and if this limit is equal to f of a, then we say the function is continuous at x is equal to. So when we say fx is continuous at x is equal to a, if right hand limit at a of the function fx, left hand limit at a of the function fx, and value at a, these three values are same, then we say that the function is continuous at x is equal to a. This is actually the previous topic of calculus 1, that is a topic of first term, that when the function is continuous at x is equal to a. So when the function is continuous at x is equal to a, if right hand limit is equal to left hand limit is equal to value. And now we have to find the limit of x tends mod x, that is fx as x tends to a, right hand limit, left hand limit, and value at a. So limit x tends to 0 of fx is what? Limit x tends to 0 of mod x, and is mod 0. First find either right hand limit, limit x tends to 0 plus mod x is 0, and limit x tends to 0 minus mod x is 0, and f of 0, value of f of 0 is what? Mod 0 is 0, and therefore limit x tends to 0, fx exists, and it is equal to f of 0, and therefore fx is equal to mod x is continuous at x is equal to 0. So this function mod x is what? Is continuous at x is equal to 0, but mod x is not differentiable at x is equal to 0, and therefore we have the counter example for the statement that if the function is continuous, then we cannot say the function is differentiable at that point. So continuity does not imply differentiability, but the converse is true, that if the function is differentiable at some point, then function is continuous at that point. But the converse is not true, that if the function is continuous, then it may or may not be differentiable at that point. So this is the counter example, fx is equal to mod x. This function is continuous at 0, but is not differentiable at 0. That is, the continuity does not imply the differentiability. Next is theorem. Prove that every differentiable function is continuous, but converse is not true. That is, if the function is differentiable, then function is continuous at that point. But converse is not true. Prove that if the function fx is differentiable at x is equal to c, then it is continuous at x is equal to c. What is about converse? That is, the converse is not true actually. That is, if the function is differentiable, then function is continuous. But the converse is not true. That is, if the function is continuous, then it may or may not be differentiable at that point. For example, mod x is continuous at x is equal to 0, but mod x is not differentiable at 0. But if the function is differentiable, then it must be continuous. So we have to show that every differentiable function is continuous. For this, every differentiable function is continuous. So assume that the function fx is differentiable at point x is equal to c. Now we have to show the function fx is continuous at x is equal to c. So the function fx is differentiable at x is equal to c by definition of differentiability. This is the definition of differentiability. What we have? We have that F.C. is equal to, F.C. is equal to limit x tends to c, fx minus f of c divided by x minus c. This limit exists. Why this limit exists? Because the function fx is differentiable at x is equal to c. Our assumption is that fx is differentiable at x is equal to c, and therefore this limit exists, and F.C. is equal to this limit. Okay, and this limit exists because of the function definition of differentiability of the function. So as the function is differentiable, we have this. Now to prove fx is continuous at x is equal to c, that is, we have to show limit x tends to c of fx exists and is equal to f of c. When we say fx is continuous at x is equal to c, we know that the definition is what? Limit x tends to c fx exists and is equal to f of c. And now consider, we have to show this. Consider the limit x tends to c of fx minus f of c. So we start with from this. Now we have to show this, that limit x tends to c fx exists and is equal to f of c. So for that, start from this step, that consider limit x tends to c fx minus f of c. Then limit x tends to c, multiply and divide by x minus c, this factor. Multiply by x minus c and divide by x minus c. Now limit of a into b is limit of a into limit of b. So limit of a minus limit of b is limit of a minus limit of b. So limit of fx minus limit x tends to c of f of c is equal to limit of this factor, that fx minus f of c divided by x minus c, into limit x tends to c of x minus c. Because limit distribute over addition, subtraction, division, multiplication straightforward. That is, limit of fx into gx is limit of fx into limit of gx. So we have this, and therefore limit x tends to c fx, limit x tends to c f of c is itself f of c. So right, limit x tends to c fx, f of c is f of c, f of c, because limit is on x and this f of c is what? if the function of c is not the function of x, it is free from x, and so this f of c is constant with respect to limit, because limit is on x, and this is the constant function f of c. So it is limit is itself f of c. Then limit of this factor, limit x tends to c, fx minus f of c divided by x minus c is f dash c by using this equation, because f is the function fx is differentiable at c. So we have this, that f dash c is this, and therefore we have the guarantee of the existence of this limit. We have the guarantee of the existence of this limit, and it is equal to f dash c, because our assumption is that function fx is differentiable at x is equal to c. So we have the value of this quantity is f dash c, and then limit x tends to c of x minus c. So substitute x as c, so c minus c is 0. So this is 0. By assumption means the value of this quantity as f dash c is by using assumption. This is our assumption, that value of this limit is f dash c. So we have limit x tends to c fx, and limit x tends to c of f of c is f of c is equal to f dash c into 0 is 0, and therefore we have limit x tends to c fx is equal to shift this quantity f minus f of c to RHS, and this means f of x is what is continuous at x is equal to c. Why? Because limit x tends to c fx is equal to f of c. This is the definition of continuous function. So this limit exists and it is equal to f of c, wherefore fx is continuous at x. But the converse of this theorem is not true, that every continuous function is not differentiable, not necessarily differentiable. That is, if the function is continuous at some point, then it may be differentiable or it may be not differentiable at that point. So for justification of this statement, write this example that fx is equal to mod x, is this function is what? Is continuous at x is equal to 0, but not differentiable at x is equal to 0. That is, the function is continuous at some point, then it may be not differentiable at that point. So the definition of derivative is this: f dash x is equal to limit x tends to c fx minus f of c divided by x minus c. Substitute x minus c as h, and so x is c plus h, and then as x tends to c, h tends to 0, because if x is c, then value of h is what? C minus c, that is 0. And so f dash c is equal to limit h tends to 0, f of, right, x as c plus h minus f of c divided by h. So this is the another definition, another form of this definition. F dash c is limit x tends to c f x minus f of c divided by x minus c, or right, f dash c is equal to limit h tends to 0, f of c plus h minus f of c divided by h. Or if you replace a c by x, then what we have? F dash x is what? Limit x tends to 0, f of x plus h minus fx, right here, not c, fx, right, fx as c as x, f of x plus h minus f of x divided by h. So this is the another form of the definition of differentiability. Already by using this definition, all the in the 12th standard, we are already given the proof of all standard rules. What are that? That if fx is x raised to n, then f dash x is what? N x raised to n minus 1. And if we take f of x as x cube, then its derivative is what? 3x square. 3x square is the derivative. So we will give the proof of x cube. Fx is x cube, then f dash x is what? 3x square. So f dash x is what? Limit h tends to 0. I use this definition. H tends to 0. F of x plus h minus fx divided by h. So write f of x plus h. Fx is x cube. So f of x plus h is what? X plus h bracket cube minus fx is x cube divided by h. And what is the x plus h cube? A plus b cube is what? A cube plus 3 a square b plus 3 ab square plus b cube. So x plus h cube is what? X cube plus 3x square h plus 3x h square plus h cube minus x cube. So minus x cube and minus x cube get cancelled. We have the remaining 3 terms divided by h, and divided by h separately to all the terms. We have 3x square, 3x by h square by h is h cube by h is h square. And then take limit as h tends to 0. Right here, x, no, it is not x tends to 0, h tends to 0, h tends to 0. Right here, h, right here, h, right here, h, right here, h tends to 0. Then substitute h as 0. So 3x square is constant now with respect to limit. So its limit is itself 3x square. But limit of this 3x into h is 0. So 3x into 0 is 0. H square, 0 square is 0. So right here, h tends to 0. It is not x tends to 0, h tends to 0, right? H tends to 0. And therefore f dash x is what? 3x square. So already these proofs are already in your 12th notebook, that if x raised to n, then the same proof, that is x plus h raised to n minus x raised to n, right? X plus h raised to n, and we have the answer n x raised to n minus 1. So in the same procedure, prove all the rules of derivative, that is fx is sin x, then f dash x is cos x, fx is log x, then f dash x is 1 by x, fx is e raised to x, then f dash x is e raised to x. So prove all these rules. Also, the chain rule is there, that if fx is tan square x, then its derivative is what? 2 tan x into derivative of tan x, that is sec square x. 2 tan x into sec square x, derivative of tan square x. Derivative of x square is just 2x, but derivative of tan square x is not 2 tan x. It is 2 tan x into derivative of tan x. It is the chain rule. If fx is log sin x, then its derivative is what? 1 by sin x into cos x. Derivative of sin x is what? Cos x. The derivative of log x is 1 by x, but derivative of log sin x is not just 1 by x. It is 1 by x into derivative of sin x, that is cos x, that is cot x. So write all the rules of derivative and give their proof like this by using this definition, that f dash x is equal to limit h tends to 0 f of x plus h minus f x divided by h. So write all the rules of derivative first here, and then give the proof of all the proofs, all the examples by using the definition. That is the derivative of the function by using definition. So we will see the next topic, that character order theorems for differentiable function, in the next lecture.